So our next speaker is Ella Podvalny, and she uses she, her pronouns. She's currently a postdoc at NYU in the lab of Bayu He, and she's going to talk about her recently published Emcee study where she's linking pupil size to arousal. Bring it on. Samantha, you have to stop sharing your screen for...
Oh, sorry.
No worries.
There. All right.
Perfect, thank you.
Now I should be able to. All right, should be on. Hi everyone, thank you very much for joining us today. And I'm very happy to talk about this work about arousal states and how they shape perceptual decisions. Actually, this everything, all the results here that I'm going to present are new. They were not included in the paper that was published last year. So, yeah, this manuscript will be out soon. But if you are interested, please email me and I will send you the manuscript. Yeah, and this work was done with Lina King and Viegen. So arousal state is a very powerful predictor of human and animal behavior. And this is especially evident, of course, when we look at the extreme arousal states, such as a deep sleep, or extremely active behavior, such as fight or flight response. And this type of behaviors are modulated by brainstem neuromodulatory systems, which also affect the pupil size. So the pupil size gets larger with heightened arousal state. And also there are many projections from brainstem to cortex. So neuromodulation also affects the frequency content of cortical population activity. And with higher arousal, we have more higher frequency fluctuations. And of course, there is a lot going on in between. In intermediate arousal states, our pupils still fluctuate all the time, and there are changes in frequency content of cortical population activity. And interestingly, all this happens even when there is no stimulus present at all and when we don't move at all. And this kind of states we usually refer to as tonic arousal. And this is what I'm going to focus on today. So more specifically, I'm going to show you some results of our recent investigation into the question of how spontaneous variation in tonic arousal influence future decisions and how arousal-linked cortical spectral power is involved in this process. So to address this question, I recorded magnetoencephalography, MEG activity in human participants, and I use eye tracker to record the pupil size. And this was done in both resting state and in perceptual decision-making task. So the first thing that I could see that using resting state and also pre-stimulus baseline, where only the participants needed only to fixate on a cross, I was able to calculate the spectral power in all frequency bands across the whole brain and to see how it changes together with pupil size. So here we already see this gradient that we expected in delta band, where we have decrease of this low frequency activity together with arousal and increase in gamma activity with arousal. And there is something more interesting going on here in between. And to quantify this better, I use an atlas of resting state networks. And for each network, I calculated the mapping between the power and the pupil size. So, and here we can see, looking at it more closely, we can see that there is this interesting inverted U-shaped relationship with pupil size and alpha power. And I'm going to use now these mappings between pupil-linked arousal and cortical spectral power to understand how they affect behavior. Now, my very simple assumption of what is state-dependent behavior is to say that behavior is a function of a stimulus that is presented and a state before stimulus onset, the state of the brain. Now, to make this very simple, the state fluctuates, as we said, this tonic arousal state fluctuates spontaneously, even without any stimulus present. So this I cannot control, but I can keep the stimulus constant. So when I keep the stimulus constant, making the link between the state to behavior would be easier. To understand how the state influences behavior, I will also look into the shared contribution of pupil-linked arousal, of the correlation between pupil size and the spectral power, but also I can think about additional neural mechanisms that regulate the pupil size, and also there are additional neural mechanisms unrelated to arousal that regulate the spectral power in cortical population activity. So I'm going to dissociate between all this. Right, so here is my task. So I use object detection task where the subjects need to report whether an object is present in the image and what is the object category. And before this main experiments begins, I want to identify the image contrast such that sometimes the subjects detect an object and sometimes they don't. So in the main experiment, in the end, there is on every trial I have exactly the same contrast, and it looks like some kind of foggy object. And sometimes the subjects say, "Oh yeah, I see it. I know what that is," and sometimes they don't, even though the stimulus is the same. And in addition to real objects, I also use scrambled images that preserve the low-level details, but they destroy the object itself. So I use this to quantify the false alarms. And yeah, to analyze behavior in this task, I quantify the reaction times and the accuracy of the categorization task, but also I calculate the decision detection criterion and sensitivity. So the more positive criterion is, the more conservative is the detection. Is the decision about whether there was an object or not. And the higher is with higher sensitivity, the subjects are just more readily can distinguish between signals and noise. So yeah, now I'm showing you the how these four behavioral metrics change together with pre-stimulus state. So what we see here is that with larger pupil size before stimulus onset, we have more liberal criterion, we have faster reaction times, we have increased sensitivity and increased categorization accuracy. Now, this is really interesting because even before the stimulus is presented, we can already say a lot about future behavior. I was interested to see if this pupil-linked effect can be explained by these changes in cortical power, also in the spectral power. So to do so, I basically regress out all the pupil size that I could predict from changes in spectral power across the whole cortex. And I see that the effect of pupil size on criterion and sensitivity disappears. So what this means is that these effects are very likely to be mediated, in fact, by cortical spectral power, and the effects on response time and category accuracy are attenuated. So what I was interested in next is to try to understand how residual spectral power, which is unrelated to arousal in different brain regions, and how it also, if it has additional effects on my behavioral metrics. So to do so, I again regressed out everything that is related to pupil. And what I saw is that pre-stimulus delta power in dorsal attention network that includes frontal eye field and IPS and intraparietal sulcus, and also default mode networks. These regions have additional effect on decision criterion, and this is actually mirrors results in monkeys. And also I found that pre-stimulus alpha power in visual areas negatively correlates with sensitivity. And I'll skip that. Finally, I just wanted to briefly mention that we also looked at spontaneous events of dilation and constriction. And we found this beautiful event-related activity and MEG signal, which was very similar to what was found in monkey LC, but we couldn't find any behavioral effects of this dilation and constriction events. So it doesn't matter if you present a stimulus during a dilation or a constriction. And yeah, this is the summary of my finding. It's really interesting to see how changes of arousal when nothing happens before stimulus onset, how powerful they can be to predict future behavior.
Great, Ella, that was really interesting. Thank you so much for your talk. So I have a question about how long the time period is in which you actually estimate the pupil size and also, of course, the spectral power.
2 seconds before stimulus onset. And actually we had, this task was designed specifically with understanding spontaneous activity in mind. And we made really long pre-stimulus intervals. So the pre-stimulus intervals were between 3 to 6 seconds. And this is very long for this kind of tasks. So we had wanted to have lots of time to make sure that, yeah.
No, that makes a lot of sense because, of course, these changes are much slower than what we typically test in the lab, which actually kind of leads into my next question. So in outside the lab, how relevant do you think these findings are? Like, do you think this is something that's also influences our behavior in our everyday life, let's say?
Definitely. I think, brain is this large scale system where and arousal state is never stable. So there are things that going on all the time. And whether you have a stimulus that comes to you in one moment, whether it comes in another moment, your decision might be different just because the state of the brain is different. And it's not only about the decisions, it's about also perceptual experience. And we even think that false alarms in our task, they're not necessarily just I mistakenly press the wrong button, but it could be also false perception. Like if you walk around in the fog and visibility is very low, sometimes you can see something that is not there. So I think this future understanding of how the state of the brain shapes decisions and perception is very relevant for real life. Yeah.
Cool. Yeah, it was a really comprehensive talk. I really enjoyed that. Thank you so much.